Hello friends, welcome to Pioneer of Success. This is the second lecture of the acoustic series. In this lecture, we are going to talk about the equations. We'll talk about each and every details of the equations which we generally come across in acoustic module of COMSOL multiphysics. Suppose we are working with piezoelectric transducers and we have certain equations, and what are the symbols, what are each and every term signify, that we will be talking about in this particular video. This video will be helpful to you if you have just started working with piezoelectric devices or any acoustic devices and you would like to model it with COMSOL multiphysics. Before I start today's discussion, I would like to tell that we have started a service where you can actually contact us via video call, and I would like to help you develop your model. I'll put the email ID in the description box. If you would like to talk to me, then you can write me to this email ID. So let us proceed with today's topic. So we have already initiated this discussion about piezoelectric transducer. This model is already given in the application library of COMSOL, and I will also put the previous video in the description box so that you can have a look into that video, and that will help you to understand this particular video. So here we are basically solving pressure acoustics equation, and we are solving it in the frequency domain. So before we start, let us see the equation in time domain. So I have actually taken this Wikipedia page, and if you see, this is how the pressure acoustic wave equation in time domain looks like. So this is your second order space derivative, and this is your second order time derivative, and this c square, c is the wave speed. So this is the generic form of wave equation, and here the instead of displacement we have the pressure, that is called acoustic pressure. So this is the main equation, and this is in one dimension. If we work in three dimension, then instead of second derivative will be having Laplacian. So this will be Laplacian of p, and this would remain the second order time derivative. So the solution looks like this, because this wave originates from a certain point and propagates in both the directions. So if it is going in the right hand side, it will also go in the left hand side, and that is why it has a solution like this. We have talked about this in other series, where we are talking about the mathematical significance of different equations. You may like to look at those videos as well. So let me go to the COMSOL interface. So here we are actually converting the time domain equation into frequency domain, and how to convert it? You have to convert by Fourier transformation. So we all know about this, and I have also discussed about the Fourier transformation in the mathematical series, so you would like to look at those videos as well. Here I will not be talking much about the transformation, but you have to have a transformation with a function which looks like e to the power I omega t, and if you do the transformation with this particular coefficient, then it will convert your time domain equation into frequency domain. Anyway, the equation in the frequency domain for this particular case looks like this. So you have multiple terminologies. So initially we start with the equation which COMSOL has provided, and then let us try to segregate the equation. Let us try to break the equation into different parts and try to analyze what the different parts signify. So here initially you can see there are few coefficients like rho c, this is the density. You have Pt, that is the acoustic pressure, and again Pt is taken as P plus Pb, so there might be a background pressure as well, and if it is so, then you have to add it up, and this is the original acoustic pressure, maybe coming from your source. Say you have a device and the device is getting vibrated, it is generating a kind of acoustic pressure. So that pressure will be P, and you may put the device into an environment where you have a background pressure, background acoustic pressure, and that could be rho B. So this is a generic case where you have the both. Now we have, so we have talked about this PT. Now there is a term QD. I'll talk about it. What is it? And there is another term QM. So both are the source terms, and how exactly they have come, I'll be talking about it. And there is certain thing K equilibrium square PT, and where K equilibrium is rho by C whole square. So this is not rho, this is omega. So omega is the angular frequency of the acoustic pressure, and this there is another constant Km. So things are little bit confusing. So where from this K equilibrium is coming, where from this Km is coming. So we should explore about this equation so that we understand every bit of it. So for that, what I have done is I have taken the original equation, original file of COMSOL. So there is a acoustic module, there is a PDF document. So in that PDF document they have talked about this. So I'll be exploring this particular PDF. I'll also put the PDF link in the description box so that you can have a look into this PDF file. It will be very much helpful. Keep this file with you if you are working with acoustic module. So let us initially discuss about these two terms QM and QD, which I have shown, which are there in the equation. So this QM term is called the monopole domain source. So this is a kind of sound source you may have in your system, and you may actually put this as a source term. So this is the monopole source and this is the dipolar source. So both are the source terms. So the if you look at the unit, so the unit will be Newton per meter cube. So you can see here the units are written. So units are Newton per meter cube, and the right hand side the unit is 1 by second square. So all the terms in this particular equation has an unit of 1 by second square. You can quickly have a look. So there is a Laplacian. So in the Laplacian 1 by meter square will come. There is a density rho, that will be kg per meter cube, and you have a pressure. So that pressure is a unit of Newton per meter square, and then if you calculate it, you will get 1 by second square. So in the left hand all the terms 1 by second square. So in the right hand also you should have the term 1 by second square, and this is your Newton per meter cube by rho c. So this rho c will be kg per meter cube. So as a whole you will have all the terms as 1 by second square. You can quickly do it and check it. Now this is the equation which we have shown in the Wikipedia. If you remember, this is the basic wave equation. So we should start with the basic wave equation and we should reach to the equation which COMSOL has provided. And in this process, if we can learn about all the coefficient, that actually solves our original requirement. So let us proceed. Yeah. So the page number you can note, just a minute. Yeah, the page number is 202. So this is the page number, and this is a chapter 2, pressure acoustic interface. So let us go to the 203. So here what you see, this is the Fourier transformation equation. So you can see a coefficient I omega t over E, exponential I omega t. So we replace this to convert the equation into frequency domain. So what it does is this time derivative, the second order time derivative. So if you make derivative twice, so I omega is the eigenvalue, so it will come So derivative of e to the power I omega t is equal to I omega e to the power I omega t. If you do it twice, it will be I omega square. So I omega square will be I square omega square. So I square means one negative will come. So for that, this negative term has come, and you got this omega square. So there will be no derivative, because by this one we have actually converted this second order time derivative into p into omega square. So from there it is coming, and they have actually taken two source term additionally, because this is coming from the, it may come, most of the times these terms will be 0 for your case. Suppose we are trying to solve acoustic pressure distribution for a vibrating plate. In that case, if we consider there is no source, the medium is stagnant, medium is calm, then these two terms will be 0. So I can assure you, for most of the preliminary cases, these two terms will be 0, but they are moving ahead with the generic term. That's why they are bearing these two, and they have again taken the generic term. That's why this is the Laplacian or divergence of the gradient. Instead of the only space derivative in one direction, they are going ahead with the generic term, that is three-dimensional case. So up to this we have understood. So then let us go back to page 202. So we should go to 202. We have missed it. Just a minute. Yeah, we are here now. Okay, up to that we have actually talked about, and then okay, so from omega square we are just modifying it in terms of k equilibrium, where your k equilibrium will be given by this particular formula. And now this, where from this formula is coming. So if you see that px can again be considered as pxy e to the power minus k zt. That means the wave is propagating in the z direction, or the, and it has a wave number of k z, and that is why this wave can be assumed by this equation. And then if you plug in this equation, that means divergence of gradient, so Laplacian, that basically means you are taking twice derivative of this. If you take derivative twice, then again minus ik and minus ik will come, so it will form a I square kz square. So I square is again minus 1, so minus 1 kz square. So this will come here, and if you just replace this, then this Laplacian will be not there anymore, because we have replaced this pressure form with this particular function, and in that case you will be having this equation. So basically, if I tell in a layman language, initially we have converted the time derivative by e to the power I omega t expression, and then we have converted the space derivative by this particular expression. Once you convert this two, you get rid of all the derivatives, and your equation becomes this. And this particular equation, you can actually see this k equilibrium, which is here in the, yeah, so this is the expression of k equilibrium. Now one additional requirement is, what if this particular wave is, you are solving this particular case in axisymmetric one. That means you solve for a particular plane and then you rotate it so that you can have information about a three-dimensional space. In that case, your modeling should be little bit different, and the equation should be in the cylindrical coordinates. So they have actually shown how exactly the equations are changing in cylindrical coordinate. and in cylindrical coordinate this km will be this m by r, where the expression for m and everything is given here. So what you need to do is you need to save this documentation and you have to go through this documentation, and if you go through it you will understand what would be your equation in axisymmetric case. So in axisymmetric case the equation will be similar, that means the equation which we have shown here, there will be a k equilibrium and the expression for the k equilibrium will be this, and in your axisymmetric case the expression will be this, where km will be m by r, and you will get this m from this particular equation. So here if we again look back, so this is our axisymmetric case, so we should have this particular expression of km, and again km equal to m by r, where m is the azimuthal mode number, and for this particular case we have considered km is equal to 0 because m is taken as 0, so we don't have this particular expression, so k equilibrium becomes omega by cc. So the idea was to understand the equation in a better way, to understand each and every term, so that we can actually relate our case with the COMSOL equation. Now this is the equation which we are solving for the pressure acoustics, and again I am telling this is in the frequency domain. So when you take the frequency domain, your study should also have this frequency domain. Here you can see in step 1 we have frequency domain solution. So if you go to study, you will see in the study step you have this option. This is the frequency domain. So you have multiple options basically, and you have to understand which option to be chosen for the right physics. Here we are solving frequency domain wave equation, so the default study should be frequency domain. Yeah, and in the frequency domain it will ask for the frequencies, because once you have converted your time domain equation to the frequency domain equation, then you can solve the equation for a particular frequency. If you want to solve it for different frequencies, then you have to do a parametric study. You start with a frequency 10 kilohertz, then go to 20 kilohertz, and for all the solutions you will have the results, and then you can plot for a parametric study. So those are the basic things. Now we are done with the equation. So today I have just shown you where exactly you can look back and you can learn about this equation. Maybe in this particular series, in another video, we'll be talking about those equations in a more systematic manner. But as the series continues, you will be learning more about this pressure acoustic. Okay. So now let us talk about this sound hard boundary. This is very much useful because in most of the cases we use it, and this boundary, the mathematical expression of this particular boundary is n dot this particular form is equal to 0. So where n is the normal vector. So here this is the line. So the normal vector will be in this direction. So negative y direction or positive y direction, this will be your normal vector. So the line could have been inclined as well, that's why we have taken a generic normal unit vector, and here it is the gradient of the pressure with the source term, if any. For this particular case there is no source term, so you can write away think this is the gradient of pressure. Okay, so what is it? N dot gradient of pressure. Then you have spherical wave radiation condition, where sometimes we go for PML, sometimes we go for this particular radiation form. This is exterior field calculations. So this is exactly what external pressure we have kept. For that sometimes you need to define it, like here the external field variable is defined as PEXT, and this PEXT will be defined in the definition, I guess. Let us see. Okay, somewhere it is written. I'll look back and tell in the next video maybe. Now here there is a one thing, solid mechanics. So I have talked about this particular thing. In this case again, most important part is the solid mechanics equation is also converted into frequency domain, because once you are solving in frequency domain you cannot integrate time dependent solution in the same problem. So this is very much important and we have to understand it, because we have converted into a particular frequency and that particular frequency is symbolizing a particular time scale. So at that time scale only you have to operate. You cannot operate into in a range of time, and that is why if you see, this is converted frequency domain solid mechanics equation. So again in solid mechanics, if you remember, there was second derivative of displacement. So that second derivative of displacement is second order time derivative is converted into space, converted into this omega square term, because e to the power I omega t, again if you do 2 times derivative it will become omega square into u. Then you have this electrostatics. I have already talked about it in the previous video. This is basically solving, there is a voltage applied across this, and because of that voltage, this is basically a piezoelectric material. So it will start vibrating and that vibration will be going to the solid mechanics equation, and that will again impart some force to the air which is in this particular domain, and the air will vibrate and it will create the acoustic pressure. So this is how we are solving. So I hope in this particular video we learned something about the equation, and we'll make more precise video on this equation because that will be necessary in the upcoming steps. So today I stop here and I would like to request you to subscribe to my channel for more updates.